All right. Hi, everybody. Thank you for joining. Let me introduce our speaker. Today we have Ioana Colfescu from the National Center for Atmospheric Science. She's a senior research scientist there and also a visiting science in the Department of Physics at the University of Oxford, as well as a visitor here in CISL with the Miles group, formerly AIML. So just a reminder to put your questions in Slido. The link should be in the chat. We will not be monitoring the chat. And yeah, you are ready to go, Ioana.
Thank you very much, Teja, for the introduction. Hi, everyone. I would like to start by thanking to CISL for hosting my visit, and in particular to David John, who is my host, as well as to some people who contributed to this work from the University of Oxford, Anje Weisheimer, Massimo Bolasina from the University of Edinburgh, Ed Schneider from George Mays University, and Stephen Mobbs from NCAS. So this work is about a methodology we used, a machine learning methodology to quantify ENSO sources of predictability. It has been done in collaboration with Hannah Christensen and David John Gagne. Hannah Christensen at the University of Oxford and David John Gagne at NCAR. And it is basically the first attempt of transitioning into more using machine learning as a tool for predictability. And whereas as previously I worked as a pure climate scientist. So the focus of the talk is not exclusively the machine learning, but basically the improved predictability skill we have got, and as you will see during the talk. So I just want to see, okay, just a second, okay. I'm going to start by introducing a bit about what ENSO is. Probably everyone knows, but I thought it's worth mentioning it since it is a talk with many machine learning scientists present here. So the motivation of the work is rooted into improving the ENSO predictability skill. But what is ENSO? So ENSO, or El Niño Southern Oscillation, is this large-scale, large mode of variability in the Pacific Ocean. So you can see here, this is the equatorial Pacific, and it's represented by a positive phase. So in the positive phase, the sea surface temperature here gets warmer than average in comparison to a long-term average climatology. And in its negative phase, which is called La Nina, the sea surface temperature becomes cooler than the average. So see this extension of cold temperature. It is a coupled mode of variability. So it is coupled, it has a coupling between the ocean and the atmosphere. So while the ENSO signature in the sea surface temperature is either positive or negative anomalies in the case of La Nina, for the atmosphere, there are these subsidence areas. So they are areas of sinking dry air. So in the case of El Niño, these sinking dry air parts are localized over, let's say, the north of South America and over the maritime continent, whereas during La Nina, so when we have a positive anomaly, they are shifted towards the west. So you see they shift towards the middle of the Pacific and then over Africa. This is the spatial signature of El Niño. There is a temporal signature. So what we do to construct an El Niño index is we take a box over the Pacific. There are various boxes. This is one representation of El Niño. And if we take the average in this box for a long period, this is, for example, El Niño index from NOAA. So from 1980 to 2020, then we have the positive anomalies. So you see, for example, in 1987, so 1986-87, we had a strong positive anomaly. So this was an El Niño. So the spatial pattern looked like this. Whereas we had years like close to before the 1990s where we had a strong negative anomaly. This is a La Nina. And this is what we call the ENSO index, the ENSO oscillation. And this is what I will use for the rest of the talk as like the target of what we want to predict with the machine learning model. Why is this index important? This is only one of the remote links of El Niño. So in terms of, for example, if we look at the pattern link to El Nino in precipitation. This is a composite map, again, from NOAA. And what shows here is that during the years when we have El Nino, when we have this positive anomaly, we have wet areas like over the subtropical Pacific here in the southern part. We have dry areas over Australia, the same over India. So it is very important to be able to predict this in advance because, of course, it has important implications for the society, for agriculture, and other sort of industries. So the limitations now in terms of forecasting, because I said it is important to predict El Nino, where we are currently, this is some illustration using one model. Here is a plot from Ham et al. And what you see in panel A is if we look at the blue curve, this is basically where we are in terms of predictability. And on the vertical axis, we have a correlation scale. See, this is the black line is everything above 0.5 in the correlation scale. And this is the lead time in months. So how many months in advance are we above 0.5 correlation scale? So 0.5, let's say, are we confident that we can predict with 0.5 accuracy, like 50%, that what is happening 12 months in advance? So you see, for example, if we say, can we predict ENSO 12 months in advance? The blue curve represents the all seasonal scale for a dynamical forecast system. Then we are able to predict above 0.5 with 1 year in advance, not more. As we go forward, so as we go over 12 months, the forecast scale goes under 0.5. Now, if we look, so again, this is all seasonal scale. If we look at now season by season scale, so you look here in panel C, if we say January, February, March, April, and so on, DJF, as you go up, these are target seasons, and then forecast lead months. So what this plot shows, hashed, is what is above 0.5. So if we wonder how well can we have a prediction with a scale above 0.5 for May, June, July, then you see here, if you say May, June, July, where like we are above 0.5 for up to 5 months in advance, not more. There are seasons for which the forecast is better, like for example, DJF, when ENSO is at its peak, as well as around winter, January, February, March. But for such a dynamical forecast, we have low confidence, especially for certain seasons. And what this paper did, Ham et al., is they used the convolutional neural network. So I'm moving back to plot A, and I'm looking now at the orange curve. And what they showed is that for the all season scale now, we can go, the confidence we have to predict to be above 0.5 goes to 17 months in advance when we use a convolutional neural network. So see here was again 12 months. So we added 5 months to the predictability. Whereas if we look at the season by season prediction, this is panel B. So the equivalent of this orange curve seasonally, it's here. If you compare this and this, you see, for example, May, June, July, which here was above 0.5 for 5 months, went to above 11 months in advance. So there is clearly, and they used as predictants the heat content of the ocean and the sea surface temperature. They did this forecast for separate seasons, and as I said, they used the machine learning approach. So the question then, which I decided to address is, okay, so building from this paper of Ham et al., what is the role? So their prediction was using heat content and sea surface temperature. I decided my prediction, we want to investigate how much does the meridional wind play a role for the ENSO predictive scale, and then investigate a bit if there is a separate predictability scale coming from the wind component versus the one from the sea surface temperature, because as I described, the main thing with El Nino is that it's a couple mode of variability. So it's very hard to say how much does it come from the sea surface temperature versus the wind or the heat content, the ocean dynamics. What are the main regions of importance for the predictability scale? So where does this scale come from regionally? Is it the Pacific? Is it the Indian? And so on. And then provide a mechanistic understanding of the predictability scale found, which is this last bullet point goes hand in hand with actually the previous one, where we look at the regions of importance of the predictability skill. So this is the architecture of the convolutional neural network. I am not going to get into all the details. Basically, what I'm going to mention is that the convolution, this is from the paper of Ham et al. This is their architecture. There are changes which we've done in terms of the input data. So what this convolutional neural network takes in as predictant is the sea surface temperature for 3 months before where we start predicting Nino 3.4. So this is denoted here with tau -2, tau -1, and tau -0. And then these are the convolutional filters, layers, and so on. And what we predict is 23 scalar values denoting the 3-month moving average of Nino 3.4, which I mentioned before, right? That time series from tau +1 to tau +23. And what the previous paper did is they took the sea surface temperature, so 3 months in advance, like 3 months back in time, and the heat content. What I'm going to do is I'm going to explain into the experiments, do various experiments with the sea surface content, winds, and heat content, and their combinations. So this is the architecture of the convolutional neural network. The periods, data, and variables, and resolution. So as training period, I used 1861 to 2001 and 17 CME5 models. This is different to the data that Ham et al. Used. They used more models and different models to the ones I had from CME5, but the results are similar. I used monthly anomalies. So the maps that you've seen before represent monthly anomalies for the sea surface temperature, U-wind. I did the simulations also for the V-wind, but we didn't find a significant predictability skills, so I'm not going to show that. And heat content. The heat content is represented by the average of the 300 meters sea surface temperature, the upper 300 meters oceanic sea surface temperature. The maps are 0, 360 and 55 south to 60 north, and then the resolution is 5 by 5 degrees. It's quite a coarse resolution. For the validation, I used 1961 to 2001 and then CME5 models, so the same as here, but other ensembles than the ones that I used. So it's data which was not seen before by the model. The same monthly anomalies, SST, U-wind, V-wind, the same resolution. And then for the forecast, I've used so observational data reanalysis, SODA or GODAS. It's mostly SODA because so in the initial in the study by Ham, they did a forecast on SODA and then they used transfer learning, and they used the GODAS data for another prediction. I didn't find any benefit of this transfer learning. I'm going to touch briefly on that, but yeah, it's very little difference. Indeed, they mentioned in their paper that the improvement was 1 or 2%. So yeah, that hasn't been done here. And then for an observational analysis, in which I did a lead lag regression and correlation analysis, we've used 1901 to 2012 to NTCR, and then had SST data, of course, the same variables. And then we interpolated the data to the same resolution as the one used by the convolutional neural network, which is 5 by 5 degrees. So the experiments that I did, by experiments, I mean running the convolutional neural network with different predictants, are as follows. So I used sea surface temperature and heat content initially, which represents my reference scenario. So in the model world, everything that we did, we then compared with this, because we assumed this would give the best predictability, and also for comparison to another paper, the Ham et al. The second one was sea surface temperature and U at 10 meters. So I used this as input, like the three months, tau -1, tau -2, 0, and the same for the wind, heat content and winds. And then I did the standalone predictions too for sea surface temperature, heat content, U at 10 meters and V at 10 meters. I'm not going to speak about this. We didn't get good predictability from this. The domain is the same. And then as metric, I used the correlation between the label data that we use. So the ENSO calculated for the observations and the model output, which are, so the correlation between the time series with 23 time instances in the observed and then the predicted. A note on the transfer learning, because I discussed yesterday with one of the colleagues I met at CISL. So for those who know the ham paper, this is what we obtained, the curve here. So first of all, this is the ENSO prediction from 1980, January to 2017. And so basically the prediction, so I did 40 ensemble simulations. The 40 ensemble simulations, the difference between them is we initialize the convolutional neural network with different weights, and then we take all these ensembles and we average them. And then the blue curve is the prediction, and the orange one is the label, is like our reality. And you can see here, so at the stage 1, the prediction is quite good. It's quite close to the label. And then if we have the fine tuning, it gets a bit closer. So in this case, where we had this ENSO, like the big ENSO in 1997, it gets a bit closer. So when we have just 40 ensembles, so 40 instances of initializing the weights. Now, when we used 100 ensembles, it actually, we didn't feel we got much difference from the transfer learning. So here is the simulation where we had 100 ensembles without the transfer learning, and then this is with the transfer learning, and you can see it's virtually for all the El Nino peaks. We don't really get much improvement. I mean, it's hardly anything from coming from the transfer learning. So I just wanted to point this out. In terms of quantifying the uncertainty, I didn't do that yet, but I wanted to mention it in the talk because I discussed this yesterday with one of the colleagues I've met. So in results, and so this is the ENSO correlation scale in the convolutional neural network models, and I'm going to start with this. So on the x-axis, we have the forecast lead months. So how many months in advance are we forecasting ENSO? And the correlation scale is what I showed before. So, and the 0.5 line is as before here in black. And what you can see here, the different colors represent the different combinations of variables, the prediction with different combination of variables. For example, the yellow-orange one is the sea surface temperature forecast, only the sea surface temperature. First of all, we can see here that the sea surface when we use only the sea surface temperature as a predictant, we get the 17-month scale, which was obtained in the previous paper. So we didn't need the heat content to get the same result. That I think from a computational point of view is very beneficial because you can of course run the model faster. Then the rest of the simulations have lower scales. So all of them are basically the scale is lower than the one obtained with the sea surface temperature as a predictant, quite significantly. The second best scale now, this is the all season correlation scale. The second best scale comes from the winds. And you see what happens in the wind. So we start lower than the one with the sea surface temperature. The scale goes down as everywhere else. It gets worse than all the other simulations. But then we have this increase here in the scale, which is centered at about 14 months leading to ENSO. And then the forecast scale is somehow above the rest of the scales. So I thought it was intriguing that we found this increased scale in here. And I wondered, what is happening? Is it real? Where does it come from? And it is also interesting now, if we look at the monthly correlation scale, so each panel shows is the correspondent of this curve, but for each season, so it's season by season scale. Again, the forecast lead months are on the x-axis. Starting with the sea surface temperature and heat content, so is the equivalent of the orange here, which cuts at 14 months. So it goes under 0.5 at 14 months. We get pretty good correlation scale increasing at leads up to 21 months in advance till April, May, June. We have a similar drop to the previous paper in May, June, July. And then this drop starts again increasing. So everything points out to the fact that we get a good correlation scale at leads up to 1 year in advance, and then we get something in here too. I'm saying this because I will explain later why I have reason to think that this scale comes from somehow a different component. For heat content and new wind, actually, so if we compare with this one, which again is our reference point, we get a drop and we get under 0.5 at this lead centered around 6, and then it's linearly, it contains it. So this lead, the increase or the skill being above 0.5 is lost in this band here. And we get good correlation skill for heat content and winds between 9 and 15 months, something like this. And then for the season, it's November, December, January, up to spring. So this skill seems to be maintained up to May, June, July, April, May, June. Going forward, SST and winds. So you see in SST and winds is interesting because we seem to maintain all the skill from the SST, and I'm going to go here to the SST immediately, but we seem to have a very similar structure to the SST plus heat content, but we get this gap here, which is more similar to when we have the heat content. And then similarly, the skill is somehow decreased at like somewhere in summer and then going into the fall. Interestingly, the correlation skill, so the potential for predictability is not high when we use only the heat component as the heat content as predictor. What is maintained from the previous prediction is this skill, which seems to go to up to a year in advance. And then the correlation skill around this area, which is present when we have the sea surface temperature as well as the winds, is not there. And finally, so the best skill we get seems to be for sea surface temperature alone, which is in agreement with this curve here, because you see for the all season correlation skill, we do seem to have the best skill. But then for the 10-meter wind, so what I mentioned before, I found interesting, like this correlation increase, you can see that there is all this correlation skill at leads between 11 and 19 months, which seems to be persistent between late fall and then go to early spring. And the question is this so? Since this skill is present in both the SST and the winds, the question that follows then is, and is not present in the heat content, is this skill here present because of the sea surface temperature? So is it aliased, or is it because of the coupling? Is it a standalone skill because of, for example, wind bursts, which as stochastic forcing from the atmosphere? Or yeah, what is the hypothesis we can test? And so going forward, the fact that we have the SST with an increased skill here, and then the wind maintains this, the forecast with the winds has this area of increased correlation, made me to make this hypothesis that maybe the predictability skill comes from the SST and the somehow coupled component at under 1 year or around 13 months. And then from 13 months ahead, somewhere between 11 and 21 months, there is a standalone separate component coming from the wind skill. And this gives the predictability for like long leads. And in order to test this, what I did is, so here I went into the correlation analysis. So first of all, I thought this data is based on models, but then the forecast is done on observations. So I thought if there is a potential predictability skill in the winds for ENSO, it means that we have to see something in the maps of the winds linked to ENSO that hints at the fact that there is a connection 14 to 15 months in advance between ENSO and this wind. And this curve here is an average between -5 north to 5 south, from 40 east to 80 west. So if you look on this axis, it's like you would go from east to west. And as you go on the y-axis, you are getting closer to the ENSO peak. So at 0, we have when ENSO peaks. And at -5 means we are 15 months in advance of ENSO peak. And then as we go forward, this is 15 months after ENSO. And the contours represent the correlation of 10-meter wind. And the colors represent the correlation of SST with the January, February, March, Nino 3.4. So that means is the link between the winds and the SST with the peak of ENSO. And what you can see at 0, for example, in color is the link of the SST with ENSO. So this represents ENSO. Now, this is preceded, so this anomaly in the SST is preceded by a strong correlation between the winds. So in contours, again, there is the correlation of the winds with ENSO, which is, so this correlation is about 0.7. So I thought, okay, if I'm looking, and you see this happens about 5 months in advance of ENSO, and this is where the ENSO happens. So what I did is I went back about 15 months, and I thought, well, if there is something, if there is a link between the winds and ENSO, I should see it in some kind of correlation. And what I found here is, see, there is no high correlation anywhere around here. It's like around 0, the contours are dying off. But then if I go back, this contour is 0.1, this contour is 0.2, and the contour here would be above 0.3 correlation, which out of a 0.7 correlation is quite significant. I didn't put on this plot a significance test. I have it for the final plot. So what we see here is that 15 months in advance of the ENSO peak, we have a high correlation at around 80 east between the winds and El Nino. And if we go now to a spatial map, so imagine this is a similar thing. There is the correlation. Now, if I look on a spatial map, and so here on the y-axis, you see how many months in advance of ENSO are we. So this is 21 months in advance, 20 months in advance, at 18 months in advance. Now, so in red here, there is any correlation, which is about above 0.3. So at 18 months in advance of ENSO, we get this red in the Indian Ocean. So I'm looking for an area around 80 east, because from this plot, everything hinted at 80 east. So see 80 east, it's here, it's in the Indian. Now we get something in the Indian at 80 east at 18 months in advance, and then 16 months in advance, which is more or less where I'm looking for, the lag I'm looking at, you have this big correlation in the Indian Ocean. So this seems to propagate here, and then it propagates over the Pacific, and then it propagates in the Pacific. So there is a hint that there is something happening in the Indian Ocean. And the question is this where the predictability skill comes from? And is it the wind, or is it the SST in the Indian where I'm getting the enhanced predictability skill? So I decided there will be a second set of experiments to isolate these key regions. How do I do? Okay, on time. To isolate the key regions for enhanced wind predictability. So instead of the maps that I put before in the convolutional neural network as predictants, I used maps which are limited to only the Pacific and the Indian. Then I will have a set of predictions with the map where you see the contour in yellow, a set of predictions with the map in blue, where we put predictants only over this area, and then a prediction only over the Indian. And then I took these two centers, which are linked to another mode of variability called the Indian Ocean Dipole, the IOD, because I assumed, well, because of that correlation propagating, that might be linked to the IOD. So I wonder what happens if I have, if I look at the predictability from these two centers. So here are the results from this second set of experiments. In here, you see the same correlation skills. So we always look for what is above 0.5 here. So first of all, D1, so the domain 1 is the one in yellow, Pacific and Indian. Here, the main outcome is the fact that the predictability skill doesn't seem to decrease significantly. So it loses maybe a month, maybe 2 months in comparison to all the map. So this hints at the fact that maybe there is not much predictability skill coming from the Pacific or the areas that are outside this box. However, if we look at D1, then at the monthly predictability skill the seasonal predictability skill, we do see a decrease. So this is for the sea surface temperature, which you remember before was the best. So we have this loss, which probably it is linked to the North Pacific. I am not showing here the maps, but there is it seems to be a correlation, like a wave train coming from the north of the Pacific, which is linked to this loss. For the wind predictability skill for the target season, as well as where are the winds in D1? So winds in D1, the all seasons seems to be similar to what I got before. So we don't lose much if we use only the yellow box. And here, this main center of predictability is maintained. Now, when we go down to the blue box, so it's an extended maritime continent. For D2, the SST, has a bit less predictability skill. It's the cutoff, it's at 14. And then the wind skill, it's in orange here. So there is somehow a loss, like the curve is a bit under the blue, but it doesn't seem to lose much. So it's enough, you know, to limit. So we get a very similar prediction from this area. However, the target season prediction does lose scale, especially. So again, we lose a lot here, and then we lose somehow here at the longer leads. And then for D2, for the U wind, we lose all the predictability skill here. See, there was a part coming, like, which was for November, December. So for fall up to late winter, it seems that we lose all the predictability skill. And then interestingly, if we take only the Indian Ocean, we don't get much. So we don't get anything from the sea surface temperature. However, it seems that the predictability skill, it is still enhanced, and we still have this center, which is about 15 months lead to ENSO. And then it is from March to April, May, June last. So for the IOD center, so if we go more in depth, because I showed you these 3 big boxes. So if we go more in depth now with the IOD centers, I did 2 predictions for the red box here, which is IOD West, and the red box here, which I called IOD East. It is a sort of an approximation of the IOD centers. Now, so the IOD West East winds is the blue curve, and it has the best predictability scale. It's 0.65. It goes down, and it never goes above 0.5. But you see, if you would shift this curve up on the vertical, then we would get a very similar representation of the total wind skill that I got in the first plot. So it is like a shifted prediction skill of the initial one. And is the best out of all these boxes. The IOD East plot is here. And you see, for the target season, actually, we do maintain the predictability skill centered around 13 months lead. And then the skill is good from February, March, April to April, May, June. So is this that we were looking for? And then the other curves don't seem to give much. We don't have anything from the SST above 0.5. So this and the analysis that I'm going to show in the following slides actually hint to the fact that this skill is either standalone, or that there is a mechanism through which the IOD West SST, because we don't have anything in the SST, but the wind could still be influenced by the SST in this box, and then give the predictability scale, the total one for ENSO. So the hypothesis that I made was we have an IOD West SST signal leading the IOD East winds, which in turn give the ENSO predictive skill at which we can see here. And finally, in order to test this, and there is, I did more analysis, but I think this is a good summary. So this is a regression of monthly SST, 10-meter winds, and heat content on the Nino 3.4 index during March, April, May. So basically, I wanted to see the link of all these variables with Nino 3.4 for March, April, May. I took March, April, May because it seems to be a good point where we have this enhanced predictability skill. And then the hashed areas are confidence level. And now if you look here, what happens, so we want to see, because my hypothesis was the IOD East SST forces the IOD West. I'm going to go back a second. So the IOD East SST, which is at about 40 East, is forcing the wind in the IOD West, which in turn gives the predictability skill. I think they were the opposite, but so you see here, if we go, and this on the vertical, we are showing how many months in advance of ENSO are we. And what you see here is that 22 months in advance, 2018, 16, up to 14, we have the significant correlations to this significant link of the SST with ENSO. Here in the winds, we have nothing. But then this SST, so as this SST, there is no, I mean, I couldn't say there is a propagation here, obviously. But if we see, so what happens at the same time that like at 16, this is in observations, by the way. So there is the same mechanism can be seen in observations, only that there is a difference between 2-3 months lag. So the skill that I'm finding in the observational analysis is centered at about 18, 17, whereas in the prediction is 15. Now, if we look at 40 east, at the link between U wind and Nino is nothing at 40 east, but then we have a good correlation here at 80 east. And it seems to happen to be really centered at about 18 months in advance. And then see this correlation. So this signal here seems to be clearly propagating because we can't see the same in the SST. So, and then we can't see anything in the heat content. So obviously we don't have a clear component as the prediction skill shows. Actually, we don't have a signal in the heat content, which gives the predictability. So my hypothesis is that now this sea surface temperature, it is indeed forcing or is preceding somehow the wind. So the sea surface temperature centered around 40 east is preceding the signal at 80 east, which in turn then gives the predictability skill, the total predictability skill, which we found at about 14 to 16 months in advance for ENSO. So to conclude, the mechanism is the one that I described. I think there is clearly an interplay between these IOD centers. Probably the regions and the boxes could be refined. I didn't work on that, and probably a better resolution would give more conclusive results. The wind component the wind component can be linked to the 0.5 skill found for the months between 11 and 21, depending on the season. And then, so I think, yes, this deep learning approach we used actually helped us discover this predictability skill and in a way quantified the near surface zonal winds act as a predictor here. The U wind, we didn't find anything for the V wind. And then, as I said, the long lead signal is generated by this couple wind SST mechanism originating in the Indian Ocean. And I think now in terms of next steps, I think there are lots of next steps. In part, why my visit here? I already discussed with John yesterday about hyperparameter optimization, because we didn't do that for the model. It was absolutely a first step. So probably that might give us even better skill. Why is the convolutional neural network? Why one of the main questions I couldn't answer is in the green box, we didn't get any significant skill. So the question is why the convolutional neural network didn't catch that in the Indian Ocean box, while in the same time it did get skill in the smaller boxes, which were included in the green box. I would like to work on distinguishing between how much actually the internal variability is giving this skill versus some external forcing, because here I use the SIMI5 model historical simulation. So it's everything in there, external forcing as well as internal variability. I think using daily winds and high resolution data, as well as some sort of quantifying the variance of the wind will be better as input for the convolutional neural network. And of course, there is a lot to do in linking this to the IOD and understanding that link better. Yeah, so I think that's it. I think I'm ready for questions, and thank you very much.
Great, thank you so much. Let me really quick just copy the Slido link in the chat one more time for people. If anybody has questions, put them in here and I will accept them. Thank you so much, Ioana. Great talk. Virtual applause for you. I don't see any questions quite yet, but I'm sure they're just making their way in. So
one thing to mention, so I'm still here at NCAR for 2 more days, so I'm happy to meet and discuss also in person. And it would have been good if I could have done this today, if not for the snow, but yeah.
Yeah, and for those of you who may have joined late, we did record this seminar, so it will be available for you to rewatch if you missed the beginning once we put it on our CISL YouTube channel. So it looks like we have one question from John.
No, so no, yeah. And I think John will have lots of questions about this model, as I anticipated yesterday when we talked. So no, John, no, there was no cross validation. yeah, and I, as I said, I look forward for discussing more, and especially the hyperparameter optimization and with John, where I will use his package. So yeah, forward to that.
I'll save some of my other questions for later then.
Okay, cool. Because I think it will probably be a long discussion about the model, and right, because yeah, I think there are many question marks regarding, in quantifying the uncertainty or how good the prediction is. It's linked to what we were discussing yesterday. To what extent is this linked to internal variability versus the model we used versus the suitability of the model and so on? So that's probably a very long discussion.
Well, yeah, and that's kind of why I asked you about the cross-validation, because you did do the model seed variation, which is kind of like a step towards doing that already. So
Yeah,
it'd be interesting to like kind of see where that goes.
Yes, yeah, me too. Thank you.
All right, so the next question from Kirsten is, great talk, amazing work. I'm curious if you had also looked at XAI methods to maybe confirm your proposed source of predictability.
No, so yeah, that's another that's another no. I didn't look at any XAI in parties because I think so the initial paper, they did some heat map analysis in there, and they did some the analysis was linked to some particular ENSO events. So they were like more like event by event. It was not for everything. So in a way, I think I didn't do the XAI because for me, the validation was more in using the traditional lead lag analysis, because I was not sure if I would do some XAI with like all the data or event by event, if I would get really a proper insight into the mechanism. But that is another thing that, yeah, we were discussing doing. And in part, I mean, it will hopefully come from the collaboration with David Jones' group, but no, I didn't. I just thought, well, I'll go the traditional way, and it would be very interesting to see if doing XAI, I will get the same areas of increased skill, or in the Indian, or where would that go, or to which region would that point out? Because I wonder, yeah, if it would show me the same as the regression analysis, or it would be very different, but yeah, that's something to do next. Thank you. Okay. Okay, so I'm reading Amanda's question. Do initialized long-range dynamical predictions also show a contribution from the Indian Ocean to multi-year ENSO predictability? I'm afraid I don't know to answer that, because I'm not an expert in the IOD and ENSO links. So and I didn't really work on this initialized long range dynamical prediction either. So I don't know, but I will save your question, and maybe colleagues, or maybe I think Anja Weisheimer like works on this, so maybe she could address this if but I don't know. I can't answer that question. I'm sorry, because I don't have the expertise. Okay, Kevin, in one of the earlier slides of correlation as a function of time, it looked like the SST plus winds curve was worse than both the SST and the winds curve, instead of being some sort of average. Do you have any ideas why that might be? So I wondered about that. Yes, that's a very good question. One of my hypotheses was that maybe the wind, so I don't know, I might be completely wrong about this. So I thought maybe it has to do with the convolutional neural network. And I thought, since the convolutional neural network is a pattern recognition, it might be that given the SST and the winds have such different, let's say, spectrums of variance and time-space variability, somehow putting them together, the model was not able to catch the best signal, especially in comparison to having just the SST or just the wind, when you learn like a certain type of propagation and a certain time scale and so on. But I don't know why. It's something I really wonder about, why the SST plus winds did worse, yes, than the SST. And I also I found it surprising that the SST gave the best skill, and we didn't need the heat content, but maybe that makes sense because the SST is in a way like a proxy. So yeah, I'm not sure, but my guess was it had something to do with the convolutional neural network rather than a physical mechanism, but I can't say that for sure. Yeah. Oh, I think Angie replied to the question. Yeah. Amanda's.
Thank you. Sorry, the Slido I noticed is not updating very well. So, but so far you have answered all of the questions that have popped up. I'll give it a few minutes for more to trickle in. If anybody has any other questions.
I didn't check my time for the talk. So how long did I go for? Was it 40 minutes?
Yeah, you went about like, 40, 41 minutes. Yep.
Oh, okay, good. Yeah.
Yeah, perfect timing.
I know, as I said, yeah, it was a challenge because doing a 15 minutes talk in 40 is quite something. Like it was the same as at AMS. So yeah.
Yeah, I cannot imagine that talk in only 15 minutes.
I can't. So one of them must have been really, really bad. If you give the same talk in 15 and 40 minutes, one of them must have been really bad. So yeah.
I haven't seen any more questions come in. Maybe we'll wait like 2 more minutes till like 1:50. And if there's no more questions, then we can wrap up a little bit early. Oh, here's one. John is asking, do you do any, it'll pop up in a second, hopefully, but he says, did you do any pre-processing on the data before training?
No, we didn't do any pre-processing. It was just calculating the anomalies and formatting so that it goes into the convolutional neural network. And just anomalies. So putting in the model the anomalies for the sea surface temperature and higher level winds instead of 10 meters. So I didn't think about that at all. I think yeah, it would probably be a good idea, especially. Yeah, I don't know actually, because I think our main focus was the wind bursts, and we consider the 10 meter like a good representation of the wind burst. So I didn't consider that. No, probably something worth thinking of. Yeah. Thank you.
Well, perfect. Well, if there's no more questions, then I think we can probably wrap up a little bit early. Again, this seminar was recorded, so that'll be available on our CISL YouTube channel soon. Subscribe if you're not already subscribed to that. We always put our seminars there. So with that, thank you again, Ioana. It was great to have you, and enjoy the rest of your visit at NCAR.
Thank you very much.
Yeah, I see some virtual applause for you.